Hi, my name is Dali Alnaeb, and I've recently completed a 2-year MSc program by Integrated Design from the Bartlett. Throughout my 2 years on the course, I had a chance to further deepen my knowledge and interest in computational work and design, as well as in biomaterials and their fabrication, where I got a chance to do more of that during my first year. I also got a chance to explore nutrient delivery systems through living organisms such as mycelium networks in order to green and regreen certain surfaces and facades. The work that you will see displayed here shortly is a summary of my thesis project in second year called Reswarmalytics. Currently, in the furniture and built industry, there is a heavy reliance on the use of unsustainable materials such as concrete and steel, and in the case of the furniture industry, thermoplastics. The use of such materials or the overuse of such materials to design components and objects has heavy implications on the globe through climate change. And the the major aim of visual analytics is to alleviate the damage caused by this by reimagining and redesigning components with more sustainable biomaterials. The components that are in focus here are a chair and an architectural column. It is important to note, however, that there is a certain trickiness with the redesign of components with biomaterials, as biomaterials have a significantly weaker mechanical strength than their counterparts, such as concrete and thermoplastics. And therefore, the components have to undergo a sizable geometrical transformation. And this process is done by combining two different areas of computational modeling. Algorithmic and generative design tools are combined with engineering analysis and mathematical modeling. So the components going through this rigorous methodology means that the core features of resource analytics and this thesis are in the process and the method, rather than in just the final output shapes and geometries. Resource analytics fits in well within the theme of growth and emergence, as in its generative design part, an adaptation of swarm intelligence, which was developed in the 1980s, is developed in order to fit the agenda of resource analytics. I will now share my screen to show the work as it is displayed on the vPro website. And as we can see here, these representations with lines show the custom techniques that are made for the purposes of this project. And basically, there's a large number of particles that travel through 3D Cartesian space, and their driving and steering mechanisms are a result of forces applied on them through neighboring particles, as well as external forces that obviously shape and drive the directionality and growth of the system. The particles leave behind them trails, which are then converted to geometry that represents the solid part of the model. This way of designing grants flexibility in terms of molding and redesigning shapes. So as mentioned earlier, this project is currently acting on two different scales. And the furniture scale consists of reimagining and redesigning the famous Pantone chair, which was developed in the 1960s. Obviously, the Pantone chair owes its fame due to its cantilevering seating area here, which could take loads up to 100 kilograms. The thinness of the material with such a cantilever is the chair's most extraordinary feat, and that's a result. That is as a result of its high mechanical strength. The material is a type of thermoplastic called polyurethane or polypropylene, and the chair is made possible as a result of injection molding that the material goes through. However, this project is, as you can imagine, if this chair is redesigned with a material that is significantly weaker, it might be tricky to sustain the cantilevering area. And so the first iteration, as seen on the boxes on the left-hand side here, is a modeling using the swarms in order to try an iteration that is similar to the original geometry of the Pantone chair, as can be seen here. The geometry is then taken to the other core part of the project, which is the engineering analysis part, and tested with the geometries being embedded with the mechanical properties of a biomaterial. In this case, it was a mixture of chitosan and bone. I will go into the biomaterial details slightly later. But for now, the chair can obviously be seen failing at the critical area where the cantilever is at highest stress. And the chair buckles as a result of the weight force from the 120 kilograms that the simulation was going through. So as a result, the swarms are then readjusted and re-steered in order to thicken the area of high stress. The areas are obviously dictated by the color-coded geometry, and as you can see on the right-hand side here, at the critical areas, the swarms were adjusted to thicken the base and provide a more robust foundation. The resulting geometry is obviously tested again on the engineering side to see the mechanical properties of the biomaterial in play. And as can be seen, the chair simulated as well with another 120 kilograms, but was able to sustain the loads as the total megapascal stress was on average significantly lower. So it shows that a geometrical transformation of sorts is able to realize these biomaterials in a new geometry that would function well. A large portion of this project was conducted during the global COVID pandemic, which started earlier next year. And this caused there to be much more emphasis on the rigor of the computational process in general. And as a result of not being able to be in the lab to conduct physical biomaterial tests, as students, we get access to a vast number of journals online and some novel biomaterial mixtures and papers which include a high level of specification and detail on the mechanical properties and structure of the biomaterials, allowed me to have access to a myriad of different materials to input into the analytical software, which allows for very high material detail and property specification. And this resulted obviously in a simulation of the deformation of materials as a result of the loads imposed on them with a good degree of accuracy. The analysis of the successful version of the chair resulted in a very high mass, which was obviously undesired. And to rectify this, a mass reduction treatment was applied on the geometry. And this was, in a sense, to discover how much material can be stripped down until you can still sustain 120 kilogram weight force on the chair. And so this gives a sense of where the core components are of the chair, and as can be seen here, which are down the middle of the chair. And obviously, as mentioned, the two computational modeling parts of this project are quite dynamic tools, and therefore a lot of the modeling and the analysis was developed through simulation rather than still modeling. And I will just now show the video in order to grasp the dynamic aspect of the project. As we see here, this is the mass reduction treatment, stripping the mass of up to 40% away from the chair, and therefore reconsidering the core components and remodeling the final design of the chair. The final design consists of a hybrid of two materials, which you can see here at the top part is a mixture of chitosan and bone, and with more of the chitosan in the ratio, this allowed for a slightly more comfortable sitting area for the chair. And for the structural part and the more for the core and the area that needs to sustain the load, a larger ratio of hydroxyapatite, which is the tough component of bone, forms the base of the chair in combination with gelatin. The external researchers which developed the mixture of hydroxyapatite and chitosan are H. Li and their group. And the final phase of this project is currently exploring the same, using the same method to reimagine the concrete cylindrical column with biomaterial. And the biomaterial that was chosen for this is a form of artificial bone of hydroxyapatite mixed with gelatin. And as you can see here, the cylinder is evolved into this irregular and quite eroded shape, which for this part of the project, I collaborated with a teammate, Erfan Ahmed, and this was intended, in a sense, to have a type of erosion on the column and to be able to perhaps assemble and reorient this language that has been that has emerged into a spatial configuration that would make this project be able to design spaces and keep on expanding. And so this concludes my my presentation. I would like to do a special thanks to Marcos and Javier and Brenda, who were my tutors throughout this process, and Marcos Cruz, Brenda Parker, and Javier Ruiz. And a special thanks to all the other staff involved. Thank you for listening.
Hello, my name is Erfan, and I'm going to be presenting the project Prime Mover from BioID Group. The project is a collaboration among Ian Thomas Robinson, Aurora Li, and myself. The idea of Prime Mover explores the possibility of built environment acting as a medium for growth of living organisms. With environmental crisis ahead of us, it becomes a necessity to reconsider the building methodologies and to seek for an adaptable alternative which reacts to the variation of its context. The Prime Mover aims to extend the focus of architectural design process from construction stage to its lifetime by designing growth of microorganisms in building materials. It's an integration of biocompatible materials with living components in order to transform building from a static object to an instant entity which responds, adapts, and evolves with the changes happening in its surrounding environments. The process is an interdisciplinary investigation of material studies, lab experiments, computational explorations, and to find out the proper fabrication method for a system novel as such. Now I'm going to be sharing my screen and take you through some of the steps of our process. The first section of the project kind of pivots around rigorous scientific experimentations led by Ian through testing series of different plants for extraction of plant hormones for growth of callus tissue. However, in order to be able to incorporate plant tissues into a new context, providing the hospitable environment is a must. Fragility of plant tissues in its growth and propagation push the project toward emphasizing on certain groups of hosts. This consideration kind of happened in two different layers of the way we were selecting the material and how we designed our whole system. As you can see in this diagram, the outer protective layers provide the access of nutrients through vascular network, while the absorbent inner layers reside the hormones auxin and cytokinin. This setup was structured as a non-uniform tiling system, building up a shell structure as an incubator for growth of protected plant tissues. The other diagram shows the second setup, which, similar to the first one, the maintenance of the system was considered through a vascular network causing a gradient distribution of properties in our material. Here, growth of plant tissue was designed for a more resilient type of hormone in an open system, yet depending on biocompatibility of the host, limiting us only to a group of high water content biomaterials. The common feature in all biopolymers with high water ratio is the fact that they lack the proper structural integrity for being three-dimensionalized. Therefore, it was compulsory to adjust the ingredients to achieve a configuration which possesses the necessary structural stability. But considering all adjustments, fabrication with normal robotic extrusion methods will result in collapse in geometry after adding more than a few layers upon each other due to material's relatively low compressive strength. So we had to base our fabrication process on exploiting the higher tensile strength in our material. And our first solution was to, as you can see it on the right side of the screen, was to flip the plane and extrude the trails in a kind of a gravity-based method by leaving the material in a catenary condition. The other approach was to transform the plane into vertical condition and try to weave the ink on a scaffold of anchor points, which they were in a grid configuration. However, leaving the material in a sack for a long period would cause the collapse of the woven material. And in order to avoid that breakings of the printed trails, we had to stabilize the material, and we did it by increasing its pH level right after extruding the ink and by applying the alkali on its surface. In this method, we were kind of extruding the geometry from its cross-section, where within each scaffold pattern, we could get different iteration of weaving arrangements. The limitation of the size of the cross-section that we were printing was kind of dependent on the covering area of the robotic R that we were using. And in our case, obviously the optimum size was considered as a boundary of about 600 by 600 millimeter for each unit. So in that manner, we discretize our main geometry into an array of units with the mentioned boundary, each woven on a vertical scaffold, and then to stack all those layers upon each other. By taking the printed unit out of the scaffold, anchor points will leave the hollow space for the reinforcements of the layers with the substructure. This substructure could also act as an infrastructure for irrigating the whole system for maintenance of the desired hydration rate in different parts of our geometry. Well, the image below shows a dehydrating condition of stacking three printed units together, where the scaffold anchor points are replaced with the tubes enabling the irrigation of the system. The variance of the color that you can see it in the image in the material shows the gradient of the hydration rate, which dehydrated areas, which are a bit more darker, those areas express a higher stiffness, and while the areas that you can find with higher hydration rate, they can provide a better environment for growth of our living components. So the next stage was to translate our fabrication method to design strategy for the scale-up versions. Since our extrusion method was kind of to extrude the geometry from its cross-section, we embraced the same logic for developing the whole space from an initial section by proposing an axial language for the idea of opening by reactor. In another word, each geometry was an array of units in one direction. So with the progression of the geometry in the first axis, each unit is kind of customized based on the environmental factors which were affecting the growth of our living components. The next iteration was influenced by deviating the main horizontal axis in the Z direction and by applying the varied proportion of these vectors in respect to their angle and be able to iterate skewed moments in the lengthwise progression of our geometry. So again, in the next level, we try to develop the same logic in one more layer, and the deviation of axis was also applied in Y direction to transform the main rails from a linear condition to a curvilinear state. So by replacing the main vertices of the geometry, which were located in the XY plane on a vector field, the geometry of the organized primary stage was transformed to a non-uniform setup. In addition, depending on the first state of the main grid, the intensity of the vector field in varied position, and also the number of connections branch out from each rail. This informed the deformation of the base network in order to create variation in porosity pattern in each separate unit and to facilitate the desirable hosting environment for growth of our living organisms in our open system. The next stage was to merge these two kind of actually generated blocks with the main incubator part in order to rationalize the whole idea with consideration of human interaction and spatial qualities which we're trying to make, and meanwhile to sort out of outline the juxtaposition of the two different languages in intersection moments and try to inform the main geometry. And finally, the image above shows our final proposal for a hybrid typology of space for a site in Kew Gardens. The main geometry is considered of two main languages, which the first one is considered for propagating the growth of a resilient type of plant tissue in an open system through a lattice structure, which is in conversation with an enclosed system of incubator envelope to protect the transformation of the plant tissue in a multi-layered arrangement inside our shell structure.
Hi everyone, this is Yao Meng from the BioID. So today I'm going to walk you through our group project Ozone, which is done by three ladies, me, Yan, and Chia. So our project is a design proposal for the summer installation at MoMA PS1 in New York. And this project integrates three areas of research. Environment-informed parametric design in section 1, a multi-agent system under emergence in section 2, and the application of the waste composite material in section 3. So the goal of this project is to design a biodegradable installation that responds to the local climate. So let's start viewing the project now. So starting with the first section, based on the material research, the main climatic issues affecting the biomaterial formation process are temperature, solar radiation, and wind. Then through a series of climatic studies, our findings suggested that the summer period in New York has lower wind, higher temperature, and the solar radiation. So we developed a primitive surface which applied local environmental analysis to generate the morphology of the canopy and the landscape. And the section 2 mainly explain about the application of the computational study into the landform design in this project. So the study is called the multi-agent system under emergence in the Houdini software. And these studies explored a time-based adaptability of the growth parameters, aiming at optimizing the design results to different environments. And in order to analyze how small unit action can influence the whole entity, there are three main actions takes into the consideration in the scripts, which are rotation, branching, and interaction. So each part has analyzed with various parameters to find a optimized result in terms of fabrication, contextualized application, etc. So furthermore, with data observed from material and environment, the unit structure and modular system was also analyzed and discussed under this topic as well. Composite material in the built environment. And we were using locally collected citrus peels and eggshells as raw material to create a modular building component by using robotic extrusion. So the research departs from a series of material experiments to analyze how a material composition can affect its mechanical behavior. And from this analysis, we optimized a mixing ratio and in order to achieve the extrusion under the suspending condition. So during the fabrication period, we have developed a fibrous shading component and calculated the weaving path to manage the extrusion of single module into the volume of 1 cartridge size. And this assembled prototype showing the deformation appearance when exposed to the humidity, which is also a common issue shared by all the biomaterials. Although one of the mixtures has been justified to increase the elasticity of the material, but the stability of the structure is still unpredictable. Hence, the environmental parameters which affects relative humidity, such as surface radiation and wind, became the fundamental drivers of our design. And besides, the biodegradability is one of the key contributions of this project, because most of the man-made materials can't be decomposed by the soil, and we wanted to create a synthetic material that is coming from the earth and going back to the earth by the end of its life cycle. So we wanted to use this project to introduce the biomaterial into the built industry and raise the social awareness of waste management at the community scale. So while I was collecting the raw materials for this project, the exciting moment is to see my colleagues came to school in the morning with bags of eggshells and citrus pills. And that feels like receiving Christmas presents in every other day. So thank you for watching, and I wish you enjoy the rest of the show.
Hello, my name is Aurora Li. I am one of the MArch students in BioID and one of the team members in Project Prime Mover. Prime Mover is a project developed in response to the urge of act on climate change. Through this project, we're investigating a responsive and sustainable mechanism in architecture in order to allow human-built environment to melt back to nature and to incorporate the philosophy of change and adaptation into the material of our built world. The title of the project comes from a term called unmoved mover, which is defined initially by the Greek philosopher Aristotle. It refers to the initial cause of things. So, for example, a prime mover in the engine, in the car or in the vehicle will be the engine, and in animal muscles, a prime mover will be the agonist, which is a chemical that produces biological response. It is an agent that converts energy supplied by natural force or fuel into mechanical work. And in the context of this project, we believe that buildings should be able to grow, should be able to adapt, evolve, and respond and change according to climate change, environmental change, or even cultural changes through time. And so we are defining prime mover as an inherent tendency within all life to grow, change, and transform with time. In this project, the prime mover refers to the initial cause of all these organismal activities that will happen in architecture. We have investigated using plant tissue as the material for the building. Plant tissue culture is a technology that is similar to clone technology that cultures plant from its tissue rather than using seed. This technology is mainly used in pharmaceutical fields to grow plants that are valuable for medical purposes or to preserve some of the endangered species. The growth of the tissue can be controlled and regulated by applying growth hormones to it. This means that the differentiation of the cells can be engineered artificially. So on the images showing on the screen, you can see on the left side, some of the tissue have differentiated into shoots and leaves, while the others remain still just the undifferentiated with cells with no specific functions. They have the potential to become roots or even flowers or fruit. It depends on the growth condition we create and how and what is the ratio of the growth hormone that we apply onto. So this opens up the chance of designing plant organs that normally isn't found in nature, or even to speed up or to mix some of the process and steps of the growth development in plants. So we believe that there is a potential of engineering building material from plant tissue. So this is a microscopic image of the plant callus tissue that we're actually growing in BioID lab. And this is a picture of also callus tissue, but from a different species, which is much more contaminant resistant. And also the plant tissue doesn't grow on any substrate. It have a very specific type of substrate used in plant tissue engineering, which is called hydrogel. It's a type of biodegradable polymer, and the idea is that we will make a scaffold from hydrogel, and the tissue will be growing and differentiating on top of the scaffold because it's biodegradable. So by the time the material disappears, the tissue should have already been already differentiated into, for example, roots or shoots or leaves, so that its growth should become autonomous, and then the growth can take over the previous scaffold. After it disappears, it will become the material of the building itself. And so for the maintenance purpose, to regulate the hormones that will be applied on the tissue which is growing on top of the material, we had to think about how to create a maintenance system inside the material. So this is an image of a vascular system within the hydrogel that allows moisture distributions and potentially only encourage the growth on certain parts and let the other parts just dry by itself because it's very rigid after it dried. So there's a potential of the other parts becoming a structural component in the building. So this section 1 is mainly around the idea of how to grow what is growing. This is an incubator of with all the tubes that bringing in the nutrient moistures, and inside it there will be the hydrogel scaffold, a vascularized system embedded in with the tissue culture, the tissue growing on the surface of the material. And section 2, this image is a simulation of how we're imagining the plant callus tissue to colonize the surface of a hydrogel tube. So hydrogel is a soft material which doesn't work well with compression. If we're doing additive manufacture, after a couple of layers, it will just collapse by itself because it can't support its own weight. So we had to look into other fabrication strategies to bring up the volume and to scale up and to create complex topologies in the design. So on the left side, it's this woven-based robotic extrusion, and on the right hand, the idea is that after flip the catenary will become, after the chemical reaction, which makes the material becomes a bit more rigid, the catenary will become an arch. So it's kind of like the logic of how Gaudi designed the roof for La Sagrada Familia. This is a physical model which is around 50 centimeters by 60 centimeters. It is the hydrogel, woven hydrogel, after it's solidified, we removed it from the fabrication base. So the idea is that the tissue will grow on top of the scaffold and replace the material. So the geometry of the material, the typology of the material is actually quite essential to the final appearance of the tissue. So this is an idea of how to scale up further. So we're imagining that each of the woven unit will be placed into an incubator, and each unit will be placed on top of a frame, and altogether they can become a quite big architectural component. And after the tissue matures, we will remove the incubator wall, and the tissue will become the building material itself. This is a simulation and animation of how water is running inside the vascular system and how the callus is growing on top of the hydrogel scaffold. On different growth hormone conditions, the growth of the tissue will be completely different. So it mainly shows that how the water is flowing and how the growth is happening and what kind of variety of the development a callus can have. And this is another model we made trying to convey the idea of how after the growth happens on the scaffold, what it will look like. And section 3 is mainly about the buildings, the final appearance of the building that we're imagining. So this animation shows the process of how each unit is assembled, is kind of stacked together on the frame, and gradually it starts to create space. It becomes a building. It replaces the inorganic conventional building materials that is used today. And this is another detailed image of some of the woven structures. This is another image of the detail. It's porous, it's quite intricate, it's very organic. And this image shows the idea of the building itself being the big incubator. So some of the white parts that becomes the floor or the roof or the staircase, it potentially can be the area that we're not encouraging any growth to happen. Just let the hydrogel dry, becomes a rigid and a very solid structural component. And the black parts is where we will encourage the growth of the plant tissue. So they will be placed inside this translucent panels, which are the wall of the incubator. And after the growth becomes autonomous, these walls will be removed. And this is kind of the final image of how the building or the space will look like. We're imagining the growth to take over and becomes, for example, wall or roof or ceiling of the building. It basically, the growing organism becomes the material of the building itself, and some of the parts where the growth are not encouraged, they can just stay as, for example, wall or staircase or handrails or chairs or stuff like that. So yeah, that was the project Prime Mover. I hope you enjoyed it. Bye.